both going to contribute the same. They're both strong. They're both going to dissociate 100%. Very simple. But if you have a mixture of a strong acid and a weak acid and two weak acids, then how do you deal with that process? The second one, here you would expect that, well, if this is a strong acid, this is a weak acid, most of the hydronium ion is going to come off of this. This will play very little or no role, and therefore the pH would be associated with that strong acid. But in two weak ones, then it depends on how weak they are relative to each other, right? Because if they're close, then I have to add them together. If they're far apart, then I take one and I ignore the other. Okay, and that's how we're going to start assessing the mixture of acids in this context. Okay, so just as I mentioned here, this will start with the first, so we're going to go in order here. So we'll talk the first one. We have a mixture of two strong acids. I'm going to give you a stepwise series. Those of you that had me know that when I say this, that just gives you a foundation. You don't have to actually think of it as this is step one, this is step two, this is step three. Okay? But if you want to, and it helps, especially in something that's new, then go ahead and think of it that way. So in this definition here of step one, it says calculate the millimoles of hydronium ion contributed by each acid. It does not have to be millimole, right? You can solve for the mole, combine the moles, et cetera, et cetera. The milli is only because what? I think we covered this before.
You didn't do it into the liters?
Because I have milliliters.
Right.
So instead of converting the milliliters to liters, you just make the mole millimole, millimole over milliliters, same thing.
Right.
Okay? You can do it however you want it. Whether or not you have milli there or not is irrelevant. So then you calculate the total moles or millimoles of both hydronium ion for each acid. Okay, and then from that you have your total volume. Now this is where it might change a little bit. If you have the mixture, you solve for the moles of the first strong acid, then you solve for the moles of the second strong acid. You put those moles together, but you're dividing for the molarity by the total volume. Okay? No big deal there. Just make sure that you're taking the moles of each and adding them together, then you're putting them all with the same volume. Okay? And that's your concentration, and from there you find your pH. Okay? Negative log of that concentration. So once again, this is not really that challenging. The only thing you might get tripped up on is, remember, you have to find this amount from each of the acids, add them together, and then divide by the total volume. That's all. That's really the main point here. But we're going to do an example. Okay? So I want to know the pH of this mixture of 150 milliliters of a 0.12 molar solution of HCl and a 250 mil of a 0.18 molar solution of nitric acid. So I can find the moles of each, right, as they convert. So what's the first thing you should always do if you're not sure what to do?
Equation.
Red equation. Okay, so what are we really looking at here? Let's start with the HCl. I'm going to mix that with H2O, and I'm going to form single arrow strong acid. Okay, and I'm going to form the H3O plus the Cl minus. So what am I solving for? I'm solving for how many moles of that, right? I do the same thing independently with the HNO3 plus H2O, and that's single arrow. Once again, I find H3O plus in this case NO3 minus. This is what I'm solving for. I'm solving for the moles of this and the moles of this. I'm adding them together, and then I'm dividing by the total volume.
Okay.
See, when you see it here, it should make it more clear for you as opposed to just looking at all this stuff on the, in a paragraph.
Right.
Okay. So now the HCl, I could determine that by simply saying 0.12 moles per liter. Or I could say 0.12 millimole in what they said earlier, right on that last slide, times 150 mils. That gives me my millimole. Okay. Then I do the same thing with the HCl. So that is the HCl. Then I do the same thing with the nitric acid, 250 mils times 0.18 millimole per mil. That gives me the millimoles. I add them together, and then I divide by the total volume, which is, what, 400 here? 400 mils?
Yeah.
So if I keep it in millimole, I just divide by the milliliter, and that gives me my total concentration of those two things. Once I have that total concentration of the hydronium ion, then I just put it into my pH calculation, right? Negative log of that. And that's all it's asking for is the pH here. So the thing about this is understanding, and I started you off very early, hopefully it works, to look at the equations and then see what you're doing from these. And that's going to play a bigger role as we go further, by the way. I don't know if we'll get to it today, but at some point in this chapter, this can play a big role understanding these equations. And here, if you notice, before we only dealt with one, now we're dealing with two. Right? Remember I told you that was going to happen. Out of the three examples we're going to do, where is that going to play the biggest role? The weak and the weak, right? Okay, and then you have to solve for each one of these based on the weak. How would I do that if I had a double arrow here?
With the equilibrium ice?
Equilibrium constants and stuff, right? So ice charts and things of that nature. So keep that in mind as we go further. This is the simple one. You know how to do this and this. You get the amounts of each one of those. You put that into the total concentration, and then you solve for the pH, because the pH is going to be contributed by both of these things since they're both strong acids. Okay. So let's see here. So I got 18 millimole coming off of the HCl, 45 millimole coming off of the HNO3. I add those together. I get 63 millimole. I divide by the total volume here, 400. I get 0.14 molar. That's my total hydronium concentration. So from there, I could simply solve for the pH. So the difference here between what you already know is before there was just one thing, and then you solve for the pH. Now you have two acids, so you have to account for both of those when we're dealing with strong acids. That's it. That's the only adjustment is you're doing it. You're just adding two amounts together of the hydronium ion. Okay. It looks more complicated though because there are more steps. You have to do both, not just one. That's it. There's nothing new intellectually about this, right? Other than you have to work with both. Is this okay? Everybody okay with this? If you have a question, feel free. Just because some people say it's okay, that's great. That helps me move on, but that doesn't mean that everybody feels that. So if you do have a question, that's okay to ask. And if you're not sure of the questions, then come with questions next time, right? Because sometimes it takes a minute to think about an appropriate question. You may not know the question. You know that something's not adding up for you, but you don't know how to express it. That's okay too. Just notate that, and if you don't figure out at home, either email me or come to my office or ask in class next time, right? So we could revisit things, in class as well. Step 4, throw this right in there, and I get 0.85. That's my pH. So is this a acidic solution or is this a basic solution? Very acidic, right? Yeah, absolutely. Yes. And does that make sense? I have two acids that are both strong in there. Probably going to be pretty acidic, right? Okay. Could I have also figured out if it was acidic based on this number here? Yes, what am I comparing that to? 1.0 times 10 to the minus
-3.
7.
7.
Right?
Oh yeah, 7.
If it's greater than that, then it's acidic, remember? Just, see how that helps, that little reminder, right?
Yeah.
Okay, so remember, neutral, 1.0 times 10 to the minus 7, autoionization of H2O into OH minus and H3O plus. If you have higher than that, that means you have lower than the others, since the Kw is always equal to 1 times 10 to the minus 14.
Would the hydronium ion ratio, would it ever differ from the amount of acid that you have? Like, would you ever have like 2 hydronium ions stoichiometrically? Like, would there be any difference? Or would it always be like a 1-to-1?
You mean, are you talking about, for example, if you had a polyprotic acid?
Yeah.
Because these are just binary, right? If I had a polyprotic where I had, say, H3PO4, what would happen?
And then just one would come off.
Well,
At first.
and then what would happen?
And then it would be harder to pull out.
But another one could come off, and then in that case, another one could come off. So they'd come off each separately, right? So they would still, each equation would be that same stoichiometric ratio.
Okay.
However, interesting question, because would that be the same for bases?
But bases
Calcium
all-
hydroxide.
They all come off at the same
calcium hydroxide.
Right.
Weak bases will form that hydroxide, say off an amine or a nitrogen something like ammonia, right? That will come off. That's weak, it will only produce one. But what about calcium hydroxide? Would that just separate completely
Yeah.
into two hydroxides?
Right.
So yes, when we get into bases, not here in the acids. Okay, now it's gonna, wow, that's weird. 2 weak acids. Okay, so they're going out of order, right? So we had 3 mixtures. The first one were 2 strong acids. The next one was a strong acid and a weak acid. And the third one on that list were 2 weak acids, and it looks like now they're moving to 2 weak acids. So we're skipping, I'm assuming we'll go back. If we don't, I'll give some commentary on it. All right, let's see if it follows or not. So 2 weak acids are mixed, each ionizes partially. So just like the strong acids, or you have to account for both. However, if one is more than 100-fold different, lower, then that one's not really going to be contributing much to this amount. So you only have to work with remember we called this the strongest weak acid, right? Remember we had that, we looked at it that way. At least I like to look at it that way. You don't necessarily have to. Hopefully that helps though in your interpretation of it. So if you look at the Kas of the weak acids, and of the 2 acids you have 100-fold or greater on one Ka than the other, and maybe I should stop because I know these are new topics. The higher or the lower Ka, the stronger or weaker acid. So let's go, the higher Ka, what does that indicate relative to a lower Ka?
That's the
So weaker acid.
See, it's a good thing we're going over this, right? Everybody's right. I heard the same, all of what you said filtered in the same way to me. The higher the Ka, the stronger the acid, right?
Yeah.
Okay? Because what is Ka? Remember I told you to do this before if you're ever uncertain. What is Ka? Look at this one here. I look at the Ka. What does that equal to? Over.
the yeah.
So if this is higher, that's more of this. See why I draw these things out? Very easy. Because that way if I do forget, or I don't want to spend time looking at that little bit of thing that I wrote on my paper, right? Because it's going to cost me more time to do that than just to draw this out. I'll just draw this out and then I'll make the correlation. If this is higher, this is higher. Hey, that makes plenty of sense. Stronger acid, right? So in here, the one that's higher, that's the one that's going to give the most amount of this. Because the higher means that I'm making more of that, right? So under that guideline, then, if you have one Ka that's greater 100-fold or greater than the other one, then the one that's lower isn't going to play a large enough role to contribute to the overall acidity of the solution, meaning less or very little hydronium ion compared to the stronger weak acid, so I just ignore it. I don't have to include it. Okay. That's what that's saying. And I can determine that by looking at the Kas. Okay, that's another factor here. Okay. So that we'll get to in a second. We'll do an example with this. Okay. And once again, this is all saying the same thing I just said. No big deal. Okay. Now, what if they're within that 100-fold though? That's something that's not up here. Then I have to account for both.
Yeah.
So I have to do the same thing I would do for both, and then add them together, and then divide by the total volume, just like we did with the strong acids, right? And then I go ahead and put that into the pH to determine the pH if that's what they want me to do. Okay.
Okay.
So the main thing you're looking out for is seeing whether or not it's a significant amount, and then if it is a significant amount, you factor it in, and if it's not, you wouldn't.
That's right. That's right. I mean, as an example, to put that in context, so you don't really have to think about that, right? Because let's say I have 50 millimole of this, right? Let's make these both weak, okay? Let's assume they're weak, and I get 50 millimole out of this. And I get 0.000050 millimole out of this one. When I add them together, does it matter? Nah, see, absolutely. When you see it like that, that should clarify. when you have something, we're looking at a 100-fold difference here, that's all. But when you see this here and you were to add those together, sig figs, where do you end up with anyways? It's exactly, and that's kind of that's the point of it, right? Okay. So let's see. Determine the pH and the concentration of the cyanide ion of a solution that contains 1.00 molar hydrocyanic acid with this Ka and 5.0 molar HNO2 with that Ka. Okay. When we say Ka, we're talking about the equilibrium constant of the acid. Okay. So what am I referencing when I say that? For the first one, let's say. The cyanic acid, the hydrocyanic acid, right? That's what I'm referencing. But it also means that I'm always going to have what here? The hydronium ion, if I'm calling it an acid, up in the upper half of the Ka for it. But when I say it though, and I'm doing this intentionally, by the way. If you notice a lot of the things I say, they do come back and play a role where it's maybe a little more confusing. I'm saying that this is the Ka of the cyanic acid, hydrocyanic acid. This is the Ka of the, what's that called? Nitrite acid, right? Nitrate would be NO3. If I get rid of an O, what happens to the 8? It becomes ite, right? I change the A to the I. Remember that was a Chem 101 nomenclature thing. I just noticed that because it's NO2 there, not NO3. Okay, so when I'm saying the Ka, I'm saying the Ka, I'm saying the equilibrium constant of the acid, nitrite acid, okay? So I just want to keep that clarity. But it does mean that you're going to form this, and in the equation, this is going to be on the top. So keep those two things, but they're different, right? Sometimes that's confusing. That's going to be more confusing. Hopefully it won't be now when we get to the basics. Okay, so from this, what can I do here?
Do the interline?
Go ahead.
Write the equation?
Write the equation,
And
absolutely.
then determine which is the stronger weak acid.
There's one equation. There's two equations. Okay? See that? Get really comfortable doing that. The second thing is, when I look at this, maybe I should slow down here because this is going to play a big role for the rest of this chapter. What I'm saying, write the equation just like I did here. I was only given this and this here.
Yeah.
When I'm saying I'm writing the equation, what am I really saying? What am I mixing it with? What does it form? It's always going to be mixed with water here.
Right.
That's how I'm determining where these things come from. Same thing here, right? It just says HNO2, but I have to, if I understand what I'm doing, I have to make the equation HNO2 plus the H2O.
Yeah.
Now I see this. Does everybody see that? That's really important. And that's easy to miss, right? Because listening to me, it sounds great. You're doing it. It's all of a sudden you're on an exam and you're like, wait, how do you mix this? What do you mix this with? Right? I just see HNO2. What do I do with that? I know I have to write an equation. He's drilled that into my head enough. How do I write this equation? And now I want to make sure we're on the same page. You're just putting it into water and seeing in that water, in the solution, does it form hydronium ion? And if so, how much? Okay? So the equations both have to have this plus the water. But now I have the double arrows, which changes everything, because now it's not as easy as with this here, where I had whatever amount here, that's how much I have, because it all converts to this in this ratio. Over here, am I going to have the same amount here and here? Am I going to have more or less here than here? Less, a lot less. How do I determine what that less is? Ice charge, it's an equilibrium. And guess what? I have the equilibrium constant, or the Ka.
Right.
Okay? But before I even do that, what else can I do here based on what we just learned in terms of two weak acids?
You can ignore the ACN. It's so much.
I compare the Kas. And remember, if it's 100-fold or less, I don't have to include or worry about that part of the hydronium ion formation. So is there a 100-fold or greater difference between these two?
Yeah.
Which one's larger?
On the top one.
This is the only one I need to worry about,
Right.
right? I don't need to solve for both. But if it was within that 100, then I'd have to solve for both and add them together, just like I did the strong acids. But in this case, I don't have to do that. I only have to focus on this because this is so small that the amount I produce here is going to be so little, it won't matter to the amount I'm going to produce there. And by the way, why did we skip the strong acid, weak acid if they don't put it up? Wouldn't that be the same scenario? Absolutely. I'd just worry about the strong acid and I'd forget about the weak acid. When I say weak, that implies that I have mostly reactants, right? So that's going to be, I'm going to have very few products, meaning very few of these. If it's strong, it goes all the way. I don't even care about the weak one with the strong acid. I only care about the strong acid. So in a way, a strong acid and a weak acid is much easier to determine the pH than two strong acids, because I only have to solve for one. I don't have to solve for both, right? Even though that's not overly challenging on its own for you guys. Okay, so. Now, but the thing here, it asked me for the pH. So the pH is going to be dependent on this, right? However, it's also asking me for the CN concentration in this mixture. A little bit more, right? So here I'm not just worried about the hydronium ion, but I'll solve for this first, and what will that allow me to do? It will tell me my equilibrium amounts of this, right?
Which you can then use.
And I have the Ka, so then I could solve for the rest, right?
Right.
Okay, so let's take a look. So let's start with this one. What are we trying to do here? We're trying to solve for the hydronium concentration so we can solve for the pH. I have 1 millimole of this, so I have 5 molar of HNO2. Okay, so that's good. There's my 5, 0, 0. Here you just put lines, nothing there because this is liquid. Minus X, plus X, plus X, 5 minus X, X and X. What am I going to do next?
And the X cancels out.
Put it in Ka.
Right.
I know Ka, so Ka equals X squared divided by 5, right? Because what do I do with this X?
It cancels out.
It's so small relative, right? And that was huge, so that's a big point, because that's something I brought up earlier, where do I, in a weak acid, do I make a lot of this or little relative to this?
Very
You guys said very little, hence I can get rid of that.
And a strong acid never has a K.
That's right, you don't have a K. So that started to put it together a little bit. It should be able to piece that together, right? So here's my Ka equation. I plug in this, that's equal to this. This was given. Get rid of that X, right? It's negligible. So now it's this times this square root. That's X.
Right.
Okay, no big deal. A little bit awkward here, but it comes out to 0.045 molar. So now I go back and say, what is X? X is this and this.
Yeah.
That means I just solve for this. Make sure that we understand what we're solving for when we solve for X, right? That sometimes could be challenging. So I just solve for this. This is 0.045. Therefore, now can I solve for the pH with that? Absolutely. I just negative log of 0.045. 1.35. Right? That's the pH of this mixture of 2 weak acids. That's pretty acidic, actually, when you think about it for weak acids.
Yeah.
Right? So you imagine if this is a strong acid, whatever amounts I'm starting with here, that's going to be 5 molar. You know, I do whatever, this will be 5 molar. I put in 5 molar here, that's going to be a lot stronger, right? Okay. Now, what's next here? What do I do next?
Do you account for the cyanide?
I want to find the concentration of CN, so that's the next thing I want to do. Okay, so how do I do that? Where's the equation for the CN here? Now, do I know the concentration of this? Who's given it like, what,
Yeah.
1.0 or something, 1.0?
1.
Okay. So this is 1.0, that's nothing. What is this going to start out as?
Oh, it's gonna start at 0. Oh, from the previous.
I have a mixture.
Yeah.
This is the mixture. In the mixture, we just found that it was 0.045 molar for the hydronium ion. But I don't have any of this yet. So I go negative X, plus X. Then this is going to be 1 minus that X. This is going to be 0.045 plus X, and this is just X. Okay. everybody see what happened here. We're using ice charts twice now with two different equations. But hopefully we understand how each one would have worked individually, and now collectively you're putting them together. Okay, so you're not doing anything new other than you have a more challenging problem to deal with here, right? Now you see why putting these equations up are really important. Because if you don't have those up, you're going to start going all over the place, right? But if you get these equations up, it's going to be pretty easy, because then you just follow along. Everything breaks down nicely. Now, Ka of this, do I have that?
Yeah.
That was given. That equals this times
that.
this divided by this.
Mhm.
Is this going to be high or low relative to this number?
Low.
No,
And this?
same.
So what am I going to be able to do?
Cancel them out.
Cancel them out. Absolutely. Makes it even easier, right?
Right.
All this stuff here, there's my x, that goes, that goes.
And then that divided by that times that, and then.
This times this divided by that, I have x. I don't even need to do anything else.
Yeah.
Right? Everybody see that?
Yeah.
And that's my CN concentration. Go ahead.
If you didn't see that, would you be able to just solve it the long way and still get that number?
What do you mean by the
If
long
you
way?
didn't see that, you could cancel out those two x's right there.
You can try. If you can get it in, if you can fit it into an quadratic equation, if you can square root it, who knows how it's going to come up. But yeah, you can. But you don't need to. And sometimes you might not be able to, by the way,
Okay.
depending on what happens with it, right?
Right.
Right. So this is the concentration of cyanide. And is it small?
Yeah.
Oh.
Is that what you would expect? Absolutely, right?
Because it's the weaker weak acid.
Because it's the weak acid. Very little's dissociating.
Right.
So this is exactly what you would expect. A very, very small. By the way, if I put this back in here, is this going to have any effect on that? Is this going to have any effect on this? No. That's the point. It's really, really small.
It's adding or subtracting.
Yes.
If it's being times, then it's.
Yep. Okay. Hence, that's why you assume that x is negligible, and you just cancel it out because it's irrelevant in the context of these other numbers, right? And that's what makes the whole problem much easier. Okay. Now, okay, so they didn't take us, so mixture of acids, what we looked at, and why this is set here, because we're going to do this for other things too, where we're going to do multiple different things, equations, and solve multiple different ice for different areas. I will have a problem like this probably on the exam, very similar, where you solve for the, one of the, what would I call this? Conjugate what from this?
Conjugate base.
Conjugate base. You're going to solve for the conjugate base, and you're going to solve for the hydronium concentration of the pH. So you'll have something like that. We did the strong acid. That was what we did here. Strong acid, weak acid, just the strong acid. That's how you solve for the H3O. However, if you needed to solve for the weak acid ion, then you do it this way. You would already have this, and that would just come off of doing one of these for the strong acid. Okay? If you were asked to say solve for the CN, and you mix this with HCl or HNO3 or some other strong acid. Okay? And other than that, you have no contribution of the weak acid to the overall hydronium concentration, and therefore the pH. So all you're worried about is the strong acid there. And then the weak acids, the two weak acids, we evaluated how to do that, and once again, look at the Ka. If it's greater than 100-fold, you only worry about the one that's higher for the acid component. Okay? Is that okay? Okay, because now we're going to transition, even though we're going to do something similar with these ideas here, now we're looking at polyprotic acids, meaning that there's more than one hydrogen that can come off as an acid. Okay? So here I'm looking at H2SO4, which is sulfuric acid, and when I think of sulfuric acid, do I think this is a strong acid or a weak acid?
Strong.
Sulfur is strong.
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 So now, traditionally, and out of Chem 101, this is a strong acid. And what was the rationale that you could use if you didn't know that, by the way?
OH,
There's
the relationship with the O.
2 or more oxygens per hydrogens that are acidic, right? So 4, 2, that's 2 or more oxygens per, and these are in front, so these are both acidic hydrogens. Okay. Strong. What does that mean, strong, in this case?
That is dissociates.
it's only one H coming off completely.
Right.
The
Come-
first H, polyprotic, two of them.
Right.
Is the second one strong?
No.
So when I say strong acid, I'm looking at this. So what about this? This is also an acid, right? Because this is the conjugate base
Base.
of this acid, but on its own, it's also a what, potentially?
Weak.
An acid, and more specifically, a weak acid.
Right.
So now I've just taken something that you called a strong acid, I'm saying it's a strong acid, and once it's ionized, now it is a weak acid on top of that. Okay. And how would I evaluate this after, so first this is a single arrow because that's strong, and now if I wanted to evaluate this, how would I do that?
The double arrows.
Double arrow, absolutely. HSO4 minus plus the H2O, double arrow for equilibrium, SO4 2 minus plus the hydronium ion.
Right.
But now if I was trying to figure out what the total hydronium concentration is in here to find the pH, would I worry about this part of the reaction or the second potential reaction? I have now a strong acid and a weak acid all in the same solution.
Okay.
Right?
Just confused about the 2 or more oxygens per hydrogen. So if you look at HSO4, it has 2 or more oxygens per hydrogen atom. So, but we consider that as a weak acid.
Strong. 2 or more.
No, the HSO4.
Oh, here.
Yeah.
I see what you're saying. So okay. Non-ion is what matters in terms of this
Oh,
here.
so
Now that this is an ion, this is now not, okay, this is actually the end of this chapter, if I recall.
Yeah. But you explained it on 101 too.
I did explain it in one half, so but this is actually, we're gonna get more into why. If you have the second, third, however many acid hydrogens that are coming off, after the first one, it always becomes weaker,
Right.
period. The reason is because of the orientation of where the electron densities are now within the whole molecule as they adjust by increasing the electron density around the oxygen that just lost that. Okay? Now, in this case, yes, there are 3 versus 1, but it's the second one coming off, which makes this one is now being held tighter by the oxygen it's on.
Because it's cation.
Yeah, because you've already lost a hydrogen, which in this case and usually will reflect an ion. So you can, if it's a polyprotic acid, the first one may or may not be strong, but if it's strong, every subsequent one will be weaker than it no matter what. And usually they'll be weak acids. So real quick, and I may have double bonds somewhere here and here. We're not going to get into the Lewis structure of it, but these are the 2 things I'm going to point out. This is what you're looking at. This is one acid. This would be potential another. Okay. In this case here, I have electron density here. This is pulling some of that a little bit from there. I have electron S is a little bit lower, so I have most of my electron density here, and then here, et cetera, right? This comes off. Electron density just got really high on this one. So that's going to shift these up a little bit, which is going to add more electron density to that. In that case, it's going to shift these a little bit more this way, and these and whatever else. That means that these will shift a little more here, making that a tighter bond, just to give you a sense of what's happening. So any subsequent hydrogen acid will now be much more difficult to pull off because this bond becomes stronger as the whole thing rearranges to have a more comfortable, less energetic composition. Does that make sense?
Yeah.
And so this is polypro, so the first one came off, this is automatically weak, even though it's got that proportion. You only care about that proportion in its original state. Yes. Is that okay?
Yeah.
Okay, so partial ionized, weak acid in this case, blah, blah, blah. So I could do the same things I just did with the strong and weak acid, right? We just did that mixture. This is like a mixture. So if I wanted to solve for the sulfate ion here, I could do that. If I wanted to solve for the hydronium ion and the pH, I could do that as well. Okay, okay, so here's another example where I have 2, Here's another example. Now this one starts off with only one oxygen more than the hydrogen, the acid hydrogen, so this is already a weak acid.
Right.
But I could pull off one here to get this, and now I could take this and mix it with water, and I could pull off another one, so that one's gonna be even weaker. So this is a stronger weak acid than this one, right? And that definition, you can see that by the Kas. This is much higher than this, and you can see that this one is so high that it's gonna, what, in terms of the H3O+?
It's gonna be the only one that can.
It's gonna be the only one that matters, just like you had with two weak acids. Because these are two weak acids, they're just two weak acids coming off of the same original molecule. Go ahead, Russ.
So if they just give you one equation, just by looking at it, can you be able to tell whether it will dissociate into a second weaker acid? If it's already weak, because if I just saw the first one, I wouldn't think it would dissociate again.
It will. Because you have, the Ka indicates that it will, right?
I mean, if you're not given the second equation, then, like, could you just look at the first one and know that it'll dissociate again?
Because it has another.
Yes,
Yeah.
because it has this H.
It'll always give off all of the H's.
No, none of them are giving off all the H's here.
Well, exactly, so, like,
But you are forming some of this, right?
yeah, and then at the second
Now,
step,
this now is in the system, and now it could also independently interact with the H2O, and some of it will at this level, at that Ka.
Okay,
That make sense? You see that?
so there's never gonna be like a HCO3 that doesn't react, for example? Like this reaction will occur?
This will, it just won't, not a lot. Not a lot is indicated by that really, really low Ka. But by having the Ka, it tells you something happened, automatically.
Yeah.
Yes. Something's going to happen here. How much of something is a different issue. Right, but something will. This will definitely form at some level this. But you can see very little.
Right.
Especially very little compared to this. So what do I have most, if I were to ask this kind of question, what do I have most in this sample? If I mix this is what, carbonic acid? If I mix this with water, what is going to be the predominant species in that water, using that term that you guys hated in 101 for some reason, that predominant, right? What is predominant for some reason in the lab? What would be the predominant species if I started with this and then all this went on? Still that, absolutely. That's going to be your predominant species. All the rest will just be minor, but there'll be some, and you have to account for that.
Right.
If I have this, and even though this is predominant, is this going to be a neutral, acidic, or basic solution?
Well, that
Acidic.
one would
It's
be.
going to be acidic at some level. I have the H3O plus forming. I have some forming here, but not enough to influence the overall pH. But I still have this. And am I going to have some of these and some of those?
Right.
Yes, absolutely. So what kind of question could I ask here? How much of this do I form? What's my pH? It's the same thing I just asked for a week and a week. Same thing, except for now it's all in one thing, and you would have to assume that this is going to happen, especially if you're given the Ka. The Ka is an indicator that something happened, all on its own, right? Because you have to have some concentration of this in order to have that Ka. Right. That makes sense?
Yeah.
You're just gonna have very little of it, as you can see by the actual number of the Ka.
Yeah.
Okay.
Do you have something to compare that to? Like, if I look at that, I wouldn't be able to tell if that's bigger or small number, so.
Well,
Like, is there
subsequently.
something that you compare it to, or like?
10 to the power.
Not this
So
color, right?
take me to the number, are you talking about the Ka1 and Ka2?
Yeah.
If I looked at the KAs, like, how can I tell that it's gonna mainly form, or that the reaction's gonna occur more towards the products of the reactants, or, do you know what I mean? Like,
Any weak acid, are they gonna be more product or,
it's gonna be
More reactant.
Reactant.
and if they were equal, what would they be? What would the Ka be?
It's
Neutral?
gonna be
Oh,
Oh, maybe, yeah.
So compare it to that.
Actually,
Oh, okay.
that
Is that okay? Does that give you some reference point that you're looking for?
Yeah.
So you know it's well below that. In other words, you have much more of this than this based on that number. Because remember what the Ka was. Remember, and if you're ever uncertain, write the Ka. Right? Literally, write it down. Ka, in this case, is equal to, so you have the number there, but what does it actually mean? It means this. and this is HCO3 minus, and this is H2CO3. When you see that, you automatically know the lower this is means the higher this is and the lower these are. You see now, if you have the equation, which is what you should start with, then you could automatically see those things. And then you could start making, adjustments. Is that okay? Okay. Ready to move on to, let's look at this one. Polyprotic. So here's the first one. So they're saying this one is weak, and does that make sense? Yes, I have only one more oxygen than acid hydrogens. Now that means it's going to be a certain Ka that's relatively low, but that's higher than most of the Ks we've seen, right, for weak acids. Now I have this. Is this going to have a reaction in here with the water? Yep, that's going to have a reaction. Going to take this, move it over here, mix it with water, and guess what? I'm going to form this.
Okay.
Now, this Ka going to be greater or lower than this Ka? Lower. It's
Right.
probably significantly lower, right?
Weaker.
Okay, and look at that. It is. It's a weaker acid than the first one. But am I going to have this also potentially interacting with H2O?
Right.
Absolutely. And so now this Ka is going to be much weaker than that, probably, right? Much lower, which makes it a much weaker acid. So that's the progression of getting rid of each one of the hydrogen acids.
Nice.
Does that make sense?
This is like the
Go ahead.
triprotic.
Yeah.
So if you're calculating pH here, which one would you compare to being 100-fold larger than the other? You have the highest two.
Well, yes, you're right in what you said, but if you just think about it, if you're going to make any comparison, what are you always going to be comparing it to? The one that gives the most.
Right.
So you could compare this to that and that to that. Doesn't matter. So what you said was right. Can you just compare the first two? Yes, because this is even lower than.
Obviously.
Right. That put it in perspective. So yeah, you were right. But in reality, what you really should be is that, well, if you think about it, you're comparing it all to the first one because the first one is going to give you the most amount of that. No matter what you get here, it's got to be lower than that. So yeah. Doesn't mean you should ignore it because the reason why I was careful in how I say that because these are polyprotic. So in this context, yes. But what if I had a mixture of three different acids, different weak? Now you might want to see because these two you don't necessarily know which one, and you're going to compare them, but you're still going to always compare them to the highest one.
Okay.
Yeah. That's what I was getting at. In the polyprotic one. Okay, so should be obvious. The Ka1 is the highest, then K2, then K3, and there is something that I don't know about this K4, 5, 6. They just keep getting weaker and weaker and weaker. Now,
Are the different type of acids, would that be considered the triprotic, or is that already the triprotic?
so that was just saying this, right?
Okay.
This. So then off of this, we'll just use this as the template now.
Right.
Does that make sense?
Yeah.
Okay. That's all that is. This is just higher than that, based on that. Okay. But we're talking about polyprotic.
Mhm.
Right. Basic stuff here. So here they're just going to say, we're going to talk about this more. So this is kind of odd. I wouldn't worry too much about this statement here. The loss of each hydrogen produces a negative charge, holds the other hydrogens more strongly. That's what I explained here.
Right.
And we're going to get more specific on how that works later on in this chapter. And the exam is going to have this whole chapter, not just this part. So just don't worry about this. This is just saying something to pacify you until we get to explain it a little bit later. Even though I have already given some level of explanation here. Okay. What do I have here? Ascorbic acid, H2ASC, is a diprotic acid, the H2, with this Ka and that Ka, K1, K2. What is the pH of 0.1 molar ascorbic acid? What is the concentration? Okay. What is this question, basically? We did it earlier today.
Is it strong in a week?
A week and a week,
Okay.
right? Or is it a strong in a week?
A week and a week.
How do I know it's a week in a week and not a strong in a week?
The Ka1, Ka2?
Because there's Ka.
Right.
No, and this is great. That's exactly what I want you guys to work your way through. Because it's a Ka, you know it's weak, the first one. It doesn't say strong or weak, and you wouldn't naturally know. It has ASC there. It doesn't tell you how many oxygens or whatever are there. So you can't make that simple comparison this time. but you still have indicators. And what is the indicator here? There's a Ka. The Ka automatically tells you it's weak,
Right.
right? So that's good. That's a great question because these are not intuitive things as you learn it. Now, later on, if you use this in your job or whatever, they'll become intuitive. But for now, they definitely aren't because they're new. But, and most likely, you won't have a job where you need to worry about this, so they won't be intuitive later either. But if you do, they will be. So for now, it's good to start hearing all these different ways to identify things. Not just for this type of concept, but for any concept.
Right.
Think about all the things you know and then how to correlate those things to what it is you're trying to solve for. So you actually know a lot more than you think you know about things that you are looking at for the first time, like this H2A ASC. But your instinct isn't to automatically say, oh, there's a K, it must be weak. But now, hopefully, it will be a little bit more of an instinct to do that, to identify things that you know and then place them appropriately in a new system that you're not familiar with. Okay, so can I solve for this? Absolutely. Right, what do I do?
Right on.
So what's the equation? Instead of me writing it this time, assuming you know, what would the equation be?
H2ASC plus H2O.
Thank you, 100%. H2ASC plus H2O.
Yeah.
That plus H2O, remember I just got done talking about, gives me a double arrow and I form what? Hydronium ion, which is what I'm looking for in part of it, and?
HASC.
Absolutely, HASC minus. You don't care what the ASC is, you just know that's the conjugate base of it. Who cares? That just means it's a big molecule, and who cares about the rest of it, right?
Right.
It's too much to do. Maybe it's C18, O24, H, whatever. Like, who cares, right? You just put it all together in ASC. Good enough. Because you know that nothing's happening with the ASC part, but you do know if you get rid of a hydrogen from this, you're going to have a negative charge. That's its conjugate base. So then what would be the second equation here?
Then that would be HASC plus H2O.
HASC minus.
Minus,
Yes. Plus H2O gives me ASC
Hydronium.
2 minus and hydronium.
Right.
That's it, right? So having been able to put those things together is a lot, and that's going to really matter in how I'm going to define a couple other things later, either today or next week.
Nice.
Okay, so here's the first thing. You guys got it, and there's the second thing. And you can see this is greater than 100-fold, so this is the only hydronium ion that's going to matter when I solve for the pH here, okay? So I do an ice chart here to solve for the different equilibrium concentrations of this thing. I should say, just so you have a sense of this, it's not going to factor in here, but you should kind of identify this. The more of this I make, what happens to this?
Oh, it shoots towards that side?
Yeah, it's gonna shift it a little bit this way, right? Because
Right.
this is going this way, which is pulling this out of the solution, so you'll make more of this going into this.
Right.
So this one will shift this, just to give you a general sense. But because they're so small and so little, it's not enough to really matter. I just kind of wanted you to see that there are the dynamics of what's happening within the actual reaction container,
Nice.
right? But it's not gonna actually play a role in terms of anything you're solving for.
Right.
Okay.
Theoretically.
And, yeah, right. You could. I mean, there could be scenarios. There are always exceptions to everything,
Right.
right? That's kind of why I wanted you to have a sense of that. If you were ever doing something, you had a job, and you just automatically did this without looking at your particular system, then you could be making a mistake, right?
Right.
Okay, so here, and then we're going to solve for this. So that's what we're doing over here. So then I go through my ice chart. I figure out my concentration here. I now have my, and that's concentration here. I also get my concentration of this, right? My starting concentration of this and this. I solve for my ice chart here. I have this. I can now solve for my ascorbate ion. Everybody see that? So how's this a little bit different than this is polyprotic. How's it different from the 2 weak acids at that stage? What did you have to have in the 2 weak acids that you don't have to have here?
Hydronium?
But you get that in both.
The oxygen?
From the first one. You get this here from this in both cases, whether these are 2 different weak acids or coming off of a polyprotic weak acid. I had to give you the concentration of this
Oh, okay.
in 2 different weak acids. Here I don't, because I'm getting it from here.
Yeah.
Okay, just keep that in mind. So you're lacking a piece of information, but you have it already.
You just need to-
Yes. Okay, so, okay, we know that, great. So this is everything you guys already know. Here's my first chart. That's obviously gonna be nothing, so I'm gonna do x squared over 0.10. We know this. Equals whatever that Ka was, which is this, right? So it's gonna be this times that in the square root. That's gonna give me my both this amount and that amount, since both of those are x's, which is, whoops, 2.8 times 10 to the minus 3, or 0.00028. I plug that into my pH,
With the
and I
negative
get
log?
2.55. That's just negative log this.
Oh, that, right.
So because it's the two KAs are so far apart, the X on the bottom still doesn't matter, right?
Right. And well, and that's because what's the difference that you need to have it by? 100-fold.
100-fold.
Just to keep up.
That,
So if they were 100-fold, you'd have to keep the X down there?
or would you ignore it?
No,
Or does
you
it
just
have
can't
to
get the
be-
pH yet. Because the pH will be a combination, go back,
Of
Of
two,
two.
right.
of the two.
But if
Just like,
it's-
it's just like too strong, right?
If it's 100 apart, do you ignore the X, or do
Right.
you count it in?
So here and here.
Yeah.
If it's 100 apart, you ignore the X.
Yeah, is it like equal or less than? or
You mean the
just-
K, when you put it into the Ka? And then
Yeah.
you have like this minus the X?
Yeah,
Well, this is still gonna make that X pretty small, right?
yeah.
Right.
So you can still get rid of it.
Okay.
But that's different. So the X here is just, this is whatever it is minus X. This is 0.10. The X has gotta be really small, right? Because that's a really small number. So 0.10 minus that X is gonna still give you 0.10,
Right.
So even if they're not 100-fold apart?
right?
If they're not,
But-
then you gotta add them.
whoa. Okay, hold on. So I'm saying, there are two different ideas going on here. The first one is, do you care X here, which is here, do you get rid of this X, whatever this concentration is, minus that X,
Mhm.
within the Ka of the first one?
Yeah.
Yes, because this X is gonna come out very, very small relative to what you start.
Yes.
However, this X here is still there, and you have to solve for this X and combine them in order to get to your overall H3O concentration in your pH, two different things.
Got it.
Does that make, now
Yeah.
you see where the confusion? So yes,
Okay.
you're asking about taking away the X from this, but these X's are just still very, very important in order to solve for the
And if
pH.
those two are 100-fold apart, do you still add them together, or do you just use the one that's stronger?
No, if they're greater than 100-fold, you use this one, the stronger one.
And if
If
it's
they're
equal-
closer, that's why you have to
So if
account
it's
for
equal,
both,
you-
absolutely, or something within 100.
Got it.
Right.
Yes. Yes. Is that okay? You see the difference there between those?
Yeah.
Anybody else?
When you add them, you don't do anything else other than do the.
Well, you add them
interval.
together, and then you figure out that total concentration, and then you put it into the pH to get your pH.
The
That's the
interval.
only reason you care about adding them together.
Right.
Because now they both contribute to the pH.
That one.
Right. Because they're 100-fold difference within the Kas.
Very close to.
Yeah, very close. Now, is that likely gonna happen in a polyprotic? No.
No.
Can that happen in 2 week? Absolutely.
Yeah.
Right. And that's where it would play a bigger role.
And strongly wouldn't.
A strong in a week? No. Strong is so much stronger, absolutely. But-
Typically.
well, there's no Ka. That's kind of the point. Right? It's 100% the other way.
Exactly.
That's exactly the point. Right.
Yeah.
Okay, so we're okay now?
Mhm.
Okay. So here we go. That gets rid of it. Okay. And let's go. So then we're gonna get our, did we already do it?
Mhm.
Get
Yeah.
2.8, yeah, we did, right?
Yeah.
We already got this far, and that's your pH. So this is just putting this in the negative log, you get 2.55.
Right.
How come three, it looks like 3 there and 2 there? Just to remind us.
Because for the sig.
Or the log? Because the log goes with 3.
You take how many digits there and put it after the decimal.
2 here, and the coefficient means that it goes
After the
2
decimal.
past the decimal, just a reminder.
Guess the log.
Okay, we covered it, but I want to make sure that everybody sees it again. Second time's always helpful. A little bit of reminder, just in case. Okay, now I'm calculating the ascorbate ion. So I go through this equation here, I'm looking for that. I have this, and I have this, and that was based off of right there.
Mhm.
Okay. So once again, Now I'm just gonna use Y. I could use X again, whatever. You could use K, J, whatever you want. Minus Y, plus Y, plus Y. This. This Y is clearly gonna be very, very small. Cancel, cancel, which means that these are gonna cancel, and that Y is going to be whatever what?
The
Whatever your
ASC?
K was.
Whatever the K is, absolutely, it's gonna be the same thing, right? Y equals Ka2. And usually that's going to be the case. For a polyprotic, right? Of course, 2 week, you never know what you're going to potentially have. Okay. And why is that different between polyprotic and 2 week when I say that? Because we started with the 2 week, and I already alluded to this, but I just kind of want to put this in perspective again. Got to go back here. In the second week one, is this going to be the same as this?
Right. Or is it not all?
No.
Not all.
Wait,
It's gonna be the 0, 0.
First week one it is.
This is going to be whatever it will be coming off of, right?
Oh.
But this one won't be.
yeah,
This one will be whatever the concentration you started at.
yeah.
In this case, this concentration and this are the same because it all came off of this. Okay, that same concept I put out before, so keep that in mind. 2 week will not necessarily always have the same Ka for the ion, okay? But the polyprotic usually will because they're coming off the same thing. Okay. And of course, I'm calling this Ka2 because it's the second ionization constant. And the 2 weak ones, you could potentially do that also, Ka1, Ka2, but you could also just say Ka and Ka. Ka of whatever acid it is and Ka of whatever the other acid is, which are different weak acids, not coming off the same thing. So keep those things in mind. There are a lot of parallels, but there are a couple minor differences, and this is where you're seeing them, and that's what I'm trying to point out. Okay. Okay. Now, transitioning. I hate this section. Because the acid to me is much more intuitive. The bases are less intuitive. And I'm going to take as I go through it, you'll see I'll intentionally stop and think about it so that you can see how I'm going to arrange to make sure I don't make a mistake in how I present it. Because it's very confusing in terms of the difference between Kb and Ka. Okay, so, however, strong acid, strong base, define one that ionizes completely. No big deal, obviously. That should be a pretty simple statement. Sodium hydroxide goes to sodium ion and hydroxide ion, therefore, whatever the concentration of the sodium hydroxide is, it's the same concentration in terms of its hydroxide ion because it went to 100% completion. No big deal there, right? Everybody okay with that? Okay. Here's just a little representation so that you can see that. Okay, strong bases are primarily what we're going to look at are things that have hydroxides on it. Now the problem is here you have the lithium, sodium, potassium. These are all group 1 cations, and then you have the strontium, calcium, barium. These are all group 2, and you can see one of these gives you only one OH, but one of these gives you 2 OHs. Hence goes back to that question you asked earlier. In a strong, you're going to get 2 of those per 1. Okay, and I think we did an experiment in 101 like this, right? Where I asked about the calcium hydroxide and how many hydroxides per calcium hydroxide, right? And there was 2 hydroxides. And you have to account for that. Because if I have 5 molar of this, how many moles of the hydroxide do I have?
10.
10. Right. Yes. So that's why this gets a little bit tricky. And this is what you were asking earlier. And I said not for the acid because you take each one on its own with its own equation. But in here, these break apart as strong bases completely. So you can end up with a different molar ratio that you have to account for. And that would come off of a group 2 cation. Okay? And anything primarily I'm saying here with hydroxides is going to be strong. Okay. In terms of bases, of course. Okay, so good, they're pointing this out. Produce 2, so group 2 hydroxides produce 2 moles of hydroxide per mole of the base. Something like this, okay. Unlike diprotic acids, they ionize in 2 steps. These ionize completely in 1. Only difference, not a big deal, but but you have to account for it. Okay? Not a big deal intellectually, it's a big deal in the calculation.
Sure, like, what's the reasoning? why doesn't it have steps? They just lose them together, like.
Cause the SR drops off and it just leaves the hydroxide.
Yeah.
It's like an ionic compound, calcium chloride,
Yeah.
same idea, okay? Now, okay, so here they're gonna just say as a generic base, it primarily, okay. Weak acids, weak bases, partial ionization. But if you recall, we had 3 definitions of weak bases, so let me start with that. One of them was the Brodsky-Lowry. What did that one say?
Foundation of a proton.
Okay. And I'm skipping Lewis, what did the other one, Arrhenius, say?
Formation of OH or H plus ions.
Formation of OH in water. It itself, if it's a hydroxide, separates completely, and that's where the hydroxide comes from. But that's a strong base. But if it's a weak base, like an amine or an ammonia, then it itself doesn't separate into OH.
No.
So it's not as obvious of a base, right? How did that work? It grabbed the proton from the water, and that's what created the hydroxide. And that's what the weak base is in this case, in most cases, and how we're gonna discuss it. Does that make sense? Okay. So this, if this was NH3, could take one of the hydrogens from the water, which now forms Hb plus, and left over the hydroxide ion. That's why this NH3 would be a base, because it forms hydroxide ion in water, even though the hydroxide doesn't come from itself. It comes from what it takes off of the water.
Mhm.
Okay, I want to make that's what makes it a weak base versus a strong base, which already has the hydroxide there, and it just separates and we get the hydroxide as a result of that separation. Oh, okay. So this is basically this is this, and everything else with the waters are the same, that correlation. And that's where the weak acid partially ionizes in order to, it doesn't ionize itself, it ionizes something else, in this case the water, yes. Okay, and that's the distinction of it. Okay. So the concentration, if you recall, of a strong base separates completely. So whatever it is here, it is here, and if it's coming off of a group 2, then this is double. But here, the concentration of the base, in this case here, is going to be much more than the concentration of this, the hydroxide. And that's what this statement is saying. And it's putting 1 molar there because that's what it's indicating here. If this was 2 molar, that would be 2, or whatever it is. This hydroxide concentration that comes as a result of it binding to a hydrogen in water is going to be much less than whatever the concentration of what I'm calling the base. In this case, I'm calling the ammonia the base because it's weak. If it was strong, it would either equal it or it'd be 2 times it, depending on group 1 or group 2 metals attached to the hydroxide. Okay. So base ionization, same thing. Okay, Kb, just like before, just like Ka. Except for the BH plus and the OH minus is over here and the B is there. Is that okay? When, I should bring up something here, when you look at this here, if I wanted to know what the percent ionization is here, how would I look at it? If I saw this here, how would I do that? I would take this divided by this times 100, right? That'd be my ionization. Over here,
Okay.
I would do what?
BH.
This divided by that
Okay.
times 100. Okay. Just to make
How
sure
much you have
if I'm
left?
asking about ionization. I think we did an example last lecture, or maybe even last week, but that's the ionization percent that I'm looking for. Okay. This is the base ionization constant. Of course, we want to put that, well, you can get the pKb just like before. Remember we did the pKa?
Mhm.
Seems like a long time ago now, right?
Yeah.
It's a big chapter. Right? So you also do the pKb the same way, negative log Kb. And when you do that, well, let's look at the Kb first. The higher the Kb, what does that mean in terms of the strength of the base? Stronger, just like the acid, right? Stronger. Okay. Because it means you're forming more, and here are the equations of different ones, more of this in this reaction. Okay. When I say the Kb, what am I referencing here?
Base constant of the base.
The CO3 2 minus, that's the base. Here, NH3 is the base. Here, HCO3 is the base. Okay. It's the thing pulling the hydrogen off, creating this and the hydroxide. So the higher the Kb, the stronger the weak base, right? The same way I said it with the acid. Because if you didn't have a Kb, it's already a strong base. So you don't have one, right? Okay. So this decreases strength as you decrease the Kb. So as I mentioned before, most weak bases are ammonia or amine derivatives. They look something like this. Here's your amine derivative. You have the lone pair on the ammonia. Lone pair can take this H here, causing that to fold under, giving you the 3 lone pairs on this, OH minus, and then this would be NaCN, H1, 2, 3, 4, 5, and now 6 with a plus. And that's what you get here. Same idea, you're just using the lone pair. By the way, the lone pair, where do we see that? Which definition of a base? Lewis. Exactly matches the Lewis, right? Even though in this case, you are forming this, but it could do that with something that was not necessarily, that had a hydrogen and it could bind to it, right? Like a cation, or an ion deficient molecule, like something that has boron or beryllium in the center. Make sure we recall those ideas. That's what a Lewis base was. Okay, once again, if you have Kb, you can solve for the hydroxide concentration. If you have the hydroxide concentration, you can solve for the POH, or alternatively, you can convert that to the hydronium ion and solve for the pH, depending on whatever it is it asks, right? If I had the concentration of the hydroxide, how would I get the hydronium concentration? Kw equals the concentration of the hydroxide times the concentration of the hydronium. Kw is 1.0 times 10 to the minus 14 divided by whatever the concentration of the hydroxide is, gives me the concentration of the hydronium. From that I can plug into negative log, and I get the pH. One way. Just to recall, remember these, see, this seems like a long time ago, right? Or I could just take this concentration, throw that right into negative log, and get the POH. 14 minus that gives me the pH. Okay, just small manipulations between pH and POH scales to make sure. So you can do all of that with this kind of stuff. Of course, the autoionization can be ignored because it's so small, right? So let's look at this question here. What is the pH of a 0.2 molar solution of ammonia in water? And this is the given Kb. What do I do? I would do a ice chart, right? This is equilibrium. Equilibrium, how else can I find the concentrations of things? Ice chart.
Right.
Non-equilibrium, strong, I just go straight across from the balanced chemical equation. Okay, keep those, always gonna do an ice chart. It's the only way I can do this. So I start here with, what am I starting with? 0.2 molar, 0, 0, minus X,
Plus X.
plus X,
Plus X.
plus X, 0.2 minus X, plus X, plus X equals this. X squared divided by 0.2 over minus X
Plus X is so
equals
small.
this.
Mm-hmm.
Right?
X.
Yeah. Is that going to matter?
No.
Even though if we can solve for it, if it's given, we can plug it in, of course.
Yeah.
But it's not given, so why deal with it? Just get rid of it. Makes it nice and easy. And this is this, and that equals whatever was given.
Square
This
root
times
of that.
this, the square root, that's my X. My X is also my concentration of hydroxide, which is this. Now, I could deviate, I could do one of two things, right? I could either solve for the H3O plus with the KW, or I could solve for the POH and then 14 minus that for my pH, because it asks ultimately for my pH. So here, okay, in this case, they're gonna take the KW divided by the concentration of the hydroxide. That gives me the hydronium. I plug this directly into negative log, and that's my pH, 11.28.
Sorry, could you remind me where the, number 1.0 times 10 to the negative 14 came from?
Just remember this and go back through the notes, but KW equals the concentration of, in autoionization of water, KW equals the concentration of hydronium times the concentration of hydroxide. KW is always 1.0 times 10 to the minus 14, because in autoionization of water, where it's all pure by itself, each one is neutral, so it's going to be 1.0 times 10 to the minus 7 times 1.0 times 10 to the minus 7. That's where 1.0 times 10 to the minus 14 comes from. Now when I plug something into that, it's going to adjust the balance, but the water KW will always be the same. So then whichever one you have, you take that, the KW divided by that, that gives you the other one.
Page 14 on the notes.
And that would give the pH of 14. Is that okay? Okay. So let's take a look here. We have an alkaloid, which is a naturally occurring base used to treat malaria. I get 0.0015 molar solution of the quinine. Has a pH of 9.84. What is the KB? Okay. So here is slightly different. I need to know what KB is, and what's the first thing I want to do here?
The I chart. Oh, the equation?
Do I want an equation?
Oh, no, actually the ice chart.
Can I do an ice chart without an equation?
Oh, no.
Not really.
No, no.
Right?
You don't know where to.
Because you want to know what connects to each thing.
Right.
Okay. So, what is it asking me for here? KB? Okay. So let's look at this here. I have the pH here.
Mm-hmm.
I can convert that to the POH. And from the POH, I can get the concentration of the hydroxide.
Right.
Okay. I have this here. Can I solve for KB? Can I solve the equation? What did we do with the sorbate in that equation? Did we need to know exactly what it was? No. Mhm. Okay. So, what can we do here? Well, this part's,
Yeah, so you can find your OH.
yeah, this part is just finding the OH concentration. Oops. Everybody okay with this?
Mm-hmm.
This is just, you have the pH, you can convert the pH to the POH, and then you do the anti-log of the POH, and you get the concentration of the hydroxide. That's all this is. Right? Everybody okay with that?
Mm-hmm.
Okay.
The
The
POH
key-
is always 14 minus,
What's that?
the POH is always 14 minus
pH.
pH.
If you're solving for the pH and you have the POH, then it would be 14 minus the POH gives you the pH. If you're solving for the pH or the POH and you have the pH, then it's 14 minus the pH for the POH. It depends on what you have. If you have the pH, you can solve for the POH. If you have the POH, you can solve for the pH. They're both together always equal to
14, right.
14.
Mhm.
That's the key. Okay. So here, this is the chart. This is the equation. How would you know this?
You know it's a base.
You know it's a base. You didn't know anything else, call it Q, call it QU, QUI, whatever you want, right? Doesn't matter what you call it, just like we did with the ascorbate, ASC, who cared?
Mm-hmm.
But you do know it's a base.
We're gonna grab that out.
So you can go ahead and mix it with the water, and you're gonna get the H coming off the water to form the HQU plus,
Right.
and
Right,
there's the
hydrox.
hydroxide. Now, the only other question you could really ask here, I think we did. When we talked about bases a long time, a couple lectures ago, I think I did mention something about alkaloids, right? Or did I not? Did I say that those were weak bases? Like, this is at the very beginning of the
Oh,
lecture.
yeah. Said the BR, the I, the CL.
I'll show you that before we leave today. I actually did, I think. And I'll go back and double check that so you have a reference to it. But that is representing a weak base, which is why I'm bringing that up. That's how you would have known it's a weak base, because the only thing you don't automatically know from here, it doesn't tell you it's a weak or strong base.
Yeah.
Right? When I look at this, that would be the one thing that, if I were sitting in your seat, unless I knew this was a weak base, which I think it is, I think I showed you something and I gave you little molecules on the side in like the first lecture of this chapter, like within the first 10 slides, I mentioned that.
Could you also figure out its weak base by saying what's the KB?
And because it's asking for the
So it's
KB.
like it has to be-
Absolutely, right. But in this case, it didn't give you the KB.
Yeah.
So it's a little, what,
But if
I wouldn't give you, I wouldn't trick you
Yeah.
like that, no.
I would be like, does
But
not
somebody
exist.
could, right?
Yeah,
You-
okay.
So you could find
I
a
will never
KB
do
when-
that, but somebody could, which is
Yeah.
why I'm bringing this up. It doesn't, that you can infer for sure. Like on a MCAT test, you would infer that, absolutely. That's where they always see in the questions, they'll say, infer this, you're like, infer, where would I get that from? This is one that actually might make sense if they say infer.
Okay.
Yes,
So you're saying the trick would be like if they ask you for KB even though there's none?
there's no KB.
Yeah.
So what would KB be?
None. Oh,
Zero.
Does not exist.
Yes, it wouldn't exist,
right.
right? That's a valid question if you gave a strong base.
Strong base, right.
Right.
Okay.
I wouldn't do that, but that, absolutely. That's why I say you gotta be a little careful. And I only say that because I know some of you have ambitions to go to medical school, other things, and so I don't want you to be tricked. If I say, no, I know this, and then, miss that kind of question. Be careful with those things, that's all.
Thanks.
But for me, you don't have to worry about that, no. By having that there, that does imply automatically that it's a weak base.
Okay.
But there's no other indication in here for that. Okay.
Thank
So that'd be the only thing you would be uncertain. So here I have the 0.015, 0, minus, plus, plus, this, and this is weak. You can get rid of that thing probably. What do they have here? This is just, they're telling you what it is after they went, oh, we already have this,
Yeah.
actually.
Yeah, don't you know?
We solved for that here.
Yeah. Oh,
Okay.
cool.
So we already have that, so we can plug that directly in
The
here,
hydroxide, yeah.
right? And so we can solve for this here if we want to, if it matters. You can see, well, maybe, 10 to the minus 5, you're looking at 1, 2, 3, 4, 5. It might slightly take something off there. You could plug it in. Okay.
Mhm.
So you plug in for X's here. So they did plug it in here. If you have it, you can plug it in. If you don't have it, you just cancel it out and you solve for it. And then here's your KB. So you have this over this, and that would imply that you had KB though,
Yeah.
in order to solve for that X. In this case, you don't need to. You solve for it earlier, and then you plug it in to get the KB. Okay, slightly different twist on this kind of problem, but ultimately the same ideas.
So how did you know to leave the X this time?
I had it.
Oh, because we solved for it.
Yeah, we had it. Yeah, that's the only. If you don't have it, get rid of it.
Yeah.
But then again, if you didn't have it, you would have had to already have this,
Right.
Yeah.
so that you can solve for that X, right?
And if,
If you did leave that X, would it make a big difference?
yeah.
A little bit. Once again, if you don't have X,
You can
you have to get rid of it there. And don't worry about it, you'll be fine. If you have it, just plug it in, whether it works, whether it matters or not, whatever. You have it, so just plug it in. You don't have, that way you don't have to, you're gonna spend more time trying to decide, should I keep it or not, than just doing it, right? That's why I'm saying, don't even worry. If you have it, just go ahead and plug it in. You could spend, a couple, you could start confusing yourself.
Right.
Should I not use it? And you can get into all kinds of things. If you have it, use it. If you don't. It makes it simple. You won't have any complications.
Earlier, this is backtracking just a tiny bit. Earlier, you said that when you have two hydroxides on a base, like they ionize completely, or
Mhm.
not
That's
completely,
correct.
but they
Like
happen at the
100%
same time.
ionization?
What if you have like a carbonate ion? Doesn't that turn to bicarbonate? And doesn't that turn to two different steps?
Mhm.
Because you have carbonate here, so then turns to bicarbonate, and then you have to do it again. So isn't that two steps? Or do you just only do it once?
Only when the hydroxide's strong, because it's coming off of,
Oh,
it's the hydroxide's coming from
yeah.
from the molecule itself, let's call it,
Okay,
right? In that case, the hydroxide's not coming from the molecule itself.
Mhm.
got it.
It's coming from the pulling off the hydrogen one at a
From the
time from the water.
Water, yeah.
Okay.
That's the difference, right? And that's that distinction between the strong and the weak bases.
And between acids and bases, you'd actually never have to do like a double ice chart for bases.
Right. If you have, by the way, if you had something that would make a solution acidic and something else that would make it basic,
Mm.
how would you determine if it's acidic or basic?
Find
pH?
It'd be the magnitude of each one, right?
Of the pH,
The magnitude of of how you're adjusting the hydroxide and the hydronium concentrations off of each,
Right.
right? Absolutely. Okay, so, and we're gonna get to that. That actually gets tricky, because if you really think about it, all of the conjugate bases and acids, which are weak, right, on their own, can have a reaction with water. So would that, on its own, without having the other piece that we called as an acid or base, would that also create an acidic or basic solution? Absolutely. And that's where we're gonna move towards before we start defining this kind of thing, I think, in here. So let's just, before we go, let's talk a little bit about the relationship between Ka, Kb. Okay, so here's where I'd have a Kb, right? And here I'd have so here, this would be a Ka, or this would be a Ka. I'm forming this, so that's coming off this. This would be the Kb of the inverse of that reaction. And how do they relate to each other? If I mix these two things up, what do I get?
Okay. Two waters and then.
KW. Right? So Ka times Kb equals Kw.
It's like K3 equals K1 times Kb.
What's that?
It's like from the chapter before, K3 equals K1 times Kb.
Yep. Yep, very similar. Yeah.
That is breaking down your. Cool.
But you could see here, as you cancel these things out, that's your overall equation, which is just Kw. Is that okay? This is easy, right? No big deal. Okay.
And that would equal your 14?
So of course they're inversely proportional if you want to call it proportionality. What's that?
That would be equal to your 14 with that same thing?
Yep.
Okay.
Okay, so with a little bit of time, let's do a quick example of this so we could stop at a good spot where I could pick up and hopefully finish off on
NISS quick basis.
on Tuesday, I guess. So here I have the Ka. I just simply put that Kw over Ka, this 10 to the minus 14, divided by this. That gives me my Kb. No big deal, right? All the questions are going to be just like this, right? This put in a multiple choice, though, could be a little challenging. Could make all the answers look similar. The hardest part, if I did something like this for you guys at this point, would probably be sig figs. Only because I haven't emphasized that. In 101, at the end of it, you guys would have gotten it. And at this point, I have not emphasized that at this level. But that would be probably the hardest part of this kind of question for you.
Oh, you only emphasize the
2
log
and 2,
one.
that would be 2.
Only the log one you emphasize on at this point.
Right, the log, yeah.
Yeah.
Okay, so let's a couple more quick things. Which of the following anions has the largest Kb? So this is kind of a tricky one here.
So the largest Kb value is the strongest.
Largest Kb, okay, is it,
Strongest weak base.
which means it's the strongest weak base,
Not
Right.
the strongest.
not a strong base. So what would be the acids to these I might want to evaluate? So this would be HNO3, this would be HPO4 2 minus, this
Right.
would be H2CO3.
Yeah.
Let's see if that's what they do here. Okay, conjugate acids, good, okay. Now, which one of these, is this a strong acid?
Yeah.
So then, would this have a Kb?
No.
You see how I'm doing this?
Uh,
Okay, this is interesting, right? So this is a strong acid. This doesn't, I put this in, does it bind to any H's off H2O? No. I have this here. Is this gonna come off easy or hard?
Easy.
This is the
Oh,
third hydrogen
yeah.
off of H3PO4, which is on its own a weak acid.
Yeah.
Right.
Now I go to the second one as weak. This one coming up. So is this one gonna wanna pick up?
Yeah.
Yes. This is quite a bit, right? This is gonna be very strong pull. What about this one here? This is a weak acid. Now this one,
That one's easier.
this one's already on here, so does this one, can this one pull some? Yes. Can it pull as many as this one likely? No.
So it's gonna be
Wait, what? Can you say that one more time?
Somebody else wanna explain it?
3-1.
Go ahead, Taylor. Let's
Um,
start with this one.
So that is a strong acid, and so it's gonna take all the
Ionize completely.
yeah, it's gonna ionize completely, so you don't need to worry about that.
So this one's easy, right?
Yeah.
Right.
Then it's the distinction between these two.
And between those two, the HPO4 2 minus, it's already lost all of those hydrogens through through the different stages of it, losing it, because it starts as H3PO4. And
So
so this
if I
last
get
one's
to the
really
third one,
hard to
yes.
lose. And so it's gonna wanna pick up any it can, so it's
That's
gonna
right.
be stronger.
So that means that its conjugate base is gonna be much stronger.
Yes. And like this one, that one's only lost one H, so it still wants to pick some stuff up, but not nearly as much as the HPO.
This one is going to have a much greater pull to form this than this will to form that.
It's
Because
like
this
that.
already has 2 lost hydrogens, meaning that holding on to that hydrogen is valuable to the molecule stability. So this one, this is more stable maybe than this, which is why it doesn't dissociate that much, but by losing one, it will still want to pick up a hydrogen, but nowhere near as much as this one wants to grab a hydrogen, because this, you're trying to add to the stability. It's the third one down. So this is the weakest acid or the smallest KB,
But that makes
Or
it easier
smallest
because of the
KH.
charges as well.
and this makes the largest KB,
That-
meaning the more likely to pull this one out. Now, would it be better if you had the KB charge? Yes, and I probably would. But I wanted, this is more of an intuitive question to say, well, I've lost 2 here, I'm losing 1 more. You know, the subsequent one of each one we talked about polyprotic, that's harder than this one, because this has only lost 1, this has lost 2. So this one you would assume would be harder to pull off than this one. And that's where that comes from, based on what we talked about with polyprotic. Okay, so now we'll stop here. Now, I just want to point out something. Let me see if I was right or wrong about that quinone thing. I just know that at the very beginning we did something.
Phenone?
Alkaloid, see here. Whoops, why does it do that? So and this is why it's good when you're studying to go back through things, which is why I want to show you this. Some common bases are listed here. Organic bases called alkaloids are also bitter in taste and often poisonous, and they're here. Remember when I presented this? This goes all the way back to the 8th slide in this chapter. And these ones are considered weak bases. And why? Because they have what? How do I know how do I know they're weak versus strong by looking at these pictures, which is, these are the alkaloids here. The nitrogens, they don't have hydroxide. They're not separating and giving off the hydroxide. They're creating the hydroxide through their lone pair on the end when mixed with water. Okay? So make sure when you're going through the notes and whatever, you pick up, small points. It's easy to get lost with that because we did that, 3 lectures ago?
Yeah.
Right? Who remembers that? And it was just one thing and we never talked about it again. And all of a sudden we got to a slide and we said, oh, look, we have an alkaloid. Let's assume that's a weak base. Wait, why?
That's the second,
Okay.
second page.
So yes, so keep that in mind. Okay, have a good weekend. I'll see you guys next week.